Elliot Engels. Elliot is a research associate at the University of Wollongong and Australian Synchrotron AIMSTO. Elliot obtained her PhD in medical physics and radiobiology from the University of Wollongong in 2021. She has over 25 publications, as I checked today, in diverse areas, including radiation therapy, synchrotron imaging, CT dosimetry, and nanoparticles. Her research has been recognized with several awards by the Australian Institute of Physics and Australasian College of Physical Scientists and Engineers in Medicine, including a PhD thesis award. Elliot also held several research grants from different bodies, including AIMSTO and University of Wollongong, as well as Australia Germany Joint Cooperation Scheme. And today she's going to talk about her work on developments in personalized dosimetry and imaging using phase contrast-based breast CT in preparation for clinical trials at the Australian Synchrotron, which is very much directly related to the IMPACT program. So thank you so much, Elliot, for accepting the invite for this talk, and it's over to you.
Thank you so much. That was an absolutely fantastic introduction, and I hope I can live up to it. So as you mentioned, my background is medical physics. So I will be presenting a little bit of the work I've been doing in terms of the medical physics or dosimetry behind the breast CT program. But also a little bit of imaging. So it's been quite enriching for me as a part of this project to help out and learn a lot from the imaging side as well. So yes, really my background is a lot of playing around with phantoms that look like this. This is a head phantom. And inside we're doing cell work, and you'll see microbeam tracks here on the cells, so DNA damage localized to cells. So it's a big step for me to go from this kind of thing to imaging, where we're looking at imaging a breast. So I have a kind of background for medical physics, and I take that approach coming in to understand the dose that we'll be giving to these breasts, and then hoping to get into looking at image quality and things like that. Okay, so a bit of setting the scene, I suppose, for the goal behind this work and the motivation. Of course, with the IMPACT project, we are looking to address current challenges in breast imaging. So breast cancer is the most common cancer in women, and it's detected primarily by imaging. So currently, though, we use X-rays as a mammography scan, which has generally good sensitivity, but sometimes low sensitivity for high-density breast and thicker breasts, where it becomes much harder to distinguish lesions from the existing gland material. And to get through that, you may have to supply excessive radiation doses, provide 3D images to get more information, and there can be insufficient image quality. So our goals with this work is to develop a better risk model to try and tackle this minimization of the dose as well, reduce the number of false positives in the detection of these lesions, and reduce the impact on subjects, because at the moment, to try and get through and image the breasts, they do involve painful compression. So it would be great if we could alleviate some of that patient discomfort and do our imaging in a more comfortable way for our patient. Okay, so coming into the story then is X-ray image quality and dose, the relationship. So this was the interest that I had in this, to understand the dose that the breast would be getting. And of course, then what does that mean for our imaging? Well, contrast to noise ratio, you may have heard of this one before, or signal to noise ratio, are indicators typically used for image quality, or some of the indicators used. And as you kind of improve the contrast to noise, you can distinguish certain features better against the background, as you see down the bottom. But if you can have poor signal to noise ratio, it becomes all fuzzy and not very much, you can still see the subject there, but it's much harder to distinguish from the background. So together they are linked, and in general, increasing the radiation dose reduces the amount of noise in the image, and it can increase this contrast to noise ratio and the signal to noise ratio to produce cleaner images. Now, for the breast, of course, if we're trying to identify a mass, this is also affected by the dose. So the contrast to noise will certainly be affected, and as you increase here, you can see this particular lesion becoming more and more obvious, and this is just a lesion in a breast phantom. And of course, the image interpretation is also hindered by breast density and thickness. So in that case, you can see with extremely dense breasts, as you move along here, it becomes harder and harder to see between the gland and any potential lesion inside. And we might need more dose or more angles to do so to try and resolve that. So what is the typical dose that a breast scan would involve, or a mammography scan would involve? Well, typically it's about maybe 1 gray per view, up to 3 gray per view, depending on the thickness of the breast. And as a total, you're looking at about 3 to 5 milligray is what they recommend by the IAEA for mean glandular dose. So this is the dose to what is the organ at risk within our breasts, which is the gland tissue. So that's the one we really care about, making sure the dose is low. But these requirements really vary according to the patient. And while they try and stick to 5 milligray as a mean glandular dose, there is a lot of variation in this to try and get through the breast. So for instance, compressed breast thickness, according to the paper just below, could range between many patients between 2 centimeters at the smallest, all the way up to 12.5 centimeters. And that means to be able to see through the breast, you have to give a dose of 0.3 up to 30 milligray in air just to get through the breast and actually get a good image. But they're still aiming for about 5 milligray as a maximum dose. But this is very different in terms of what the entry dose, or as you're coming from the top of the breast, is to the exit dose. And this is something I'll talk about when I'm looking at dose calculations for breasts in this talk. So I wanted to really highlight this disparity that there is in the patient breast thickness and the requirement for dose in air. It's quite a big range and a lot of variation. So what are we doing? Well, we're proposing, instead of a single planar image that I've been talking about before, or a kind of restricted tomo CT where there's not as many views, we're proposing a 360-degree view. And this is me on the robot at the Synchrotron experiencing the breast CT. So I'll get it running again. There we go. Of course, beam's not on. It's just to see how the ride goes, I suppose, and see how that comfort and looking at the experience would be for a real patient. So the idea behind our Synchrotron CT is that we could potentially get more information, combining not only the conventional kind of attenuation of the beam absorbing into the gland or the lesion material against fat, but also phase contrast CT, which actually extracts more information from the beam. And our idea is that we could then get a CT, but within the same dose that we would have a mammography done in. So that's our goal. And to see what kind of doses that we'll be getting was the goal of my work for this study. Okay. So just as a bit of a summary, so my major points here moving forward for this work was to personalize the breast CT experience in terms of accounting for different variation in patient breasts. So we want to develop an understanding of breast imaging and dosimetry for different breast sizes and composition. And this meant actually developing phantoms that could achieve that, so different sizes, different glandularity, and also looking at dose measurement in these phantoms, and then actual calculations or simulation of the dose or modeling of the dose. Then I was determining factors affecting glandular dose and image quality in patients for synchrotron CT. So these include some factors like the breast radius or the breast diameter, the beam energy that you use to get through the breast, and then the glandularity, or how many glands there are, or the breast density in the breast. And as a bit of an extra element that I've been helping on was also part of characterizing the beam line. So optimizing certain beam components like the expander, this kind of the signal in the imaging beam, so how bright the beam is, things about the robot as well in terms of the comfort, also the imaging detector and things like that. So I've been involved on many different levels, but from mostly I've been working on a canine project here at the Australian Synchrotron. So in the breast side of things, I've only dabbled a little bit in these areas. So I just wanted to show all you guys what I've been kind of dabbling in as I've been working here for breast CT. So now I'll go through and explain a little bit more what I was doing and how I did it. So the methods, all these methods were done at Hutch 3B of the IMBL. And so what they involve is that we start off here with experimental measurements. So this is dosimetry. We see the detector coming into a breast phantom here on either the CT stack here on the top or the robot. This is actually in the bed of the robot on the bottom image. And we use different beam energies, 31 to 39 kV, to do our measurements. We create with the 3T Wiggler field at the synchrotron, and we have aluminium filtration, which I denote by Ali if there's 2 lots of aluminium. Oh, the 4 is missing there. Sorry about that. Or 2√2, which is a kind of space of aluminium. And so just 1 lot of aluminium, I suppose. And I'll talk about that a little bit later, how the filtration can help our dose rate to get more dose out of the beam if we have less filtration. But that's the kind of setups we've been looking at. And of course, they're monochromatic energy. The beam is passed through a monochromator. So the dosimetry in the breast cup was done first using a PT Pharma ionization chamber. It is calibrated for air coma, so measuring that kind of dose in air, and also NDW, which can be used for water. So I was actually able to put the detector in liquid and in air and accurately read the dose that's coming in. So that meant that these breast cups could contain air, water, and fat in this testing, and the dose rate in air was reported as in milligray per second. So verification of entry and exit doses were also done. And this was, you can't do that with the pharma chamber, it's way too big. But instead we use these very small skin strip detectors called MOSKINs. And they're just silicon solid state detectors that work by integrating charge carriers. So the beam is on, making charges, and we can read out the charges according to dose. And we relate that back to the dose that we get in the pharma chamber in the middle of the phantom. But what's very useful with these strip detectors is you can put them in different positions, and they're very thin, about 5 microns actually is the active layer. And so we are able to look at entry and exit doses leaving the breast. So very, very nice. So that is a quick run through of the experimental setup of this. And then, of course, we wanted to know what was really going on in the breast model. And that was led us to the development of a Monte Carlo simulation to look at the breast. So in this case, I used GANT4 as a radiation transport simulation, Livermore physics. And here you have the beam on the left starting in space where the papa slits would be in our IMVL rooms. This is the IMVL room modeled. And here you have our breast sample downstream from there, about 1.5 meters. And then down from there, 6.2 meters away I have a fake Eiger, which I've created as a box to detect the photons. And so this simulation lets me look at how the photons are passing through my breast model here, and then how you have electrons being generated and the dose that's generated. And then all the way at the screen, I can actually calculate the number of photons that enter the screen and actually compare that to reality. So it's quite a powerful, very simple simulation, but useful when we're modeling different breast properties. So properties of the beam, it's 80 millimeters high, 222 millimeters across, polarized to represent the synchrotron beam. So our light here is polarized, and different energies, once again, we used 31 to 39 kV. All right, and so about the breast models themselves, we have different breast sizes. Here we have different breast heights, different breast radius from 4 all the way up to 10, and that's what they look like for some examples there. And of course, the material was varied. So I did air breasts as if there was no breast there, water, all the way up to from 0% to 100% glandularity within the breast. And the output, as I mentioned, we'll be looking at the energy deposited and secondary energy of the electrons that is created in the breast. And then, of course, we're looking at not only the dose of just a single projection or one beam coming in, but as if we did a full CT as well. So I'm able to look at the dose in all of those. And we look at the photon counts on my fake Eiger to kind of compare with the real Eiger and look at the efficiency of the detector. And I'm able to score secondary photons for fluorescence as well, but that's quite new and I haven't totally went down that rabbit hole yet, but that's a possibility too. All right, so that's the simulation. I've just done the experimental as well. But the last part of my methods would be what I mentioned before was me dabbling in imaging as well. So as part of that, I wanted to find a way to represent different breast glandularity, because this can be so variable between patients. And so what we did was, using a few different expanded monoenergy beams, we exposed an anthropomorphic breast phantom and imaged it. And what it's actually composed of is egg whites and lard, so that you can buy from the supermarket. And they're actually very comparable to, of course, real fat in the body. And the egg white is comparable to gland. So this became quite useful to try and see. And I wanted to see how accurate it was to a real breast in terms of the contrast and what we're able to see. And also then how well it would go at modeling real variation that we see in a real sample from the breast as well. And it lets me change the diameter of the breast. So I'll be showing you today some things from, I think it was 13 to 20 centimeter wide samples, and then glandularity from 6% up to 50% in these breasts as well. So images, all the images that I have were acquired on IGA, which is our detector at the Synchrotron. Different properties of the detector there, such as the energy threshold, frame rate that the images are acquired at. And the sample could be placed either on our robot, as you saw me on at the start, or our CT stack, which just rotates it in place, 360 degrees. And the dose, often cases, was about 4 milligray, but we did refine that in the latter images a bit more. So that is all my methods, so ranging from experimental to simulation. And without further ado, then, I'll show you what I've been up to in this realm. So to start off with, some of our results very early on was to characterize the beam. So this meant putting the detector in the field and measuring air coma. So this is looking at the rate at which our kind of photons are coming in, creating charge in air, and we're detecting that. So measured with the Farmer chamber, then what we first started out with was this kind of dose rate, millirate per second, where it peaks at around 34 keV. And then as the years went on, we really were after more flux to get brighter images so that we can actually expose for a shorter time. And so this meant putting a vacuum into Hutch 2B all the way upstream at the synchrotron. And then finally, our last one this year was to remove one of the filters, as I mentioned before. And this gave us more flux than ever before. And now, as of this year, we're going to try and get even more flux by reducing the amount of aluminium. So hopefully we will be able to increase the dose rate in air. But the best flux is typically seen with 32 keV. So this was an energy that was chosen early on to do a lot of our images because it's a nice low energy for soft tissue contrast, but also has a lot of the most flux, so we can reduce the exposure time of the patient. So that's a little bit about the characterization of our beam and what we're using in terms of our air coma. So then the next step was, okay, we have now the beam characterized for all these different energies. So now I want to understand how well this phantom could be used to estimate the simulation and vice versa. Do they relate? So if I simulate this breast model here in blue at the bottom, and I look at the entry dose, the center dose, and the exit dose, how does that compare to a jelly breast? As you see here, it wasn't water that time, but very close to water, a jelly breast, and those strip detector Moskins measuring these entry, center, and exit doses. So how does it do? Well, with the simulation, it's looking a bit like this. We're getting about more than twofold, or about at least 1.5-fold the dose at the center of the phantom. And then when we actually measure it with the Moskins, we get a very good agreement. So this is about trying to validate the simulation if we can, to prove that it's actually going to work for our needs. And we do get a really nice agreement on the entry. It's pretty much within error. And then on the exit, we're getting a much, much lower dose than the center. So well below 1 compared to the center, because of course, it's very low energy, and it's a bit tricky to get through water with low energy. So you get a quite low exit dose. And then when we did the experimental measurements, we weren't able to measure the 31 keV exit dose because there was barely anything coming through the breast at 31 keV. But we were able to measure for 35 and 38 with these detectors. It was just about the sensitivity. But again, really nice agreement. So we're feeling quite comfortable at this point to say, yes, the simulation is able to be experimentally validated. And we took that further. So in this case, again, I was looking at the dose that we measure at the center of the breast. So you see in the picture above here is the farmer chamber. That's what it looks like on the inside of that breast before. And then here it is at the center of the breast phantom in water. And we measure that to the case where it's sitting in air. And again, we find this relative dose from when it's in water to air, or in any material to air, because later I replaced it with fat as well. So dose in the material over dose in the air is what I'm calling relative dose. And I did that for the real measurement and the simulated measurement. So comparing these, so I did water to air over fat to air, and that is the pork fat that I bought from Woolies. So in that way, what I found, this is a recent measurement done this year, we found that the measured dose in water here in black compared to the simulated dose in water was actually really close. Oh, sorry, it's water for both fat there as well. So let me strike that off. Just measured dose and simulated dose. But here is water, and it's a really nice agreement again. So once again, the simulation can be validated with experimental measurements. It is behaving itself. And for fat, I'm seeing a little bit more difference, but it could be because when I measure the dose in the pork fat, it's probably different to the simulated dose, which I use adipose, because that's all that the GANT4 has to simulate fat. So it might be a slightly different composition, which might be why it's a little bit out, but definitely still within error, so we'll take it. And going further with fat, we just did a few other conditions for it. Oh, sorry, let me erase that. There we go. So different energies, again, to validate at different energies. And again, it's very close. Just getting this slight disparity, I think, because of the composition. So yeah, but overall, I was then very encouraged that the simulation that I designed was agreeing with our experimental measurements. That was a nice step in the story when, okay, I feel pretty good about that. So we'll go forward then. And this is where we're going to use what we've measured to then calibrate our simulation so that we can use any breast in the simulation and get an accurate representation of the dose. And this is called absolute dosimetry. So using the simulation and real measurements together to start to actually predict what dose will be. So how does it work? Well, you assume then from your simulation that you get your dose. And often when I'm running the sim, I've got a dose per the number of particles that were shot out. So here is our dose that you get. And in this case, it would be the dose divided by 3 particles. But in fact, I have 3 million. So often it's quite high in statistics, which is good. But that is the dose that I get from the sim. And then I say for the farmer dose that I actually measure in the phantom or in air. And in this case, I'm calibrating with air. In that way, it's just the real dose that I measure there, and I say that that's DM. So the calibration factor then to calibrate my sim will just be this measured dose divided by the simulation dose. And that tells me the number of primaries or the number of photons that I need to get exactly the same dose that I really did measure. And so I'm kind of calibrating my simulation with the experimental measurement. Yeah, so the calibration factor then is used to find the absolute dose in breasts of many different sizes, many different materials, and of course, the all-important mean glandular dose, which is the factor we're most interested in when we're actually imaging a breast to see the tolerance of the breast tissue. So as an example, here is a table showing in material, so no breast, a simulation of that. So this is made of air. And I measure the dose just here where the detector would be. And in the simulation, I get about 3 × 10⁻15 gray per primary particle. Then the measured dose is 8 milligray. And so my calibration factor in terms of the number of photons or number of primaries that I need is about 2e to the power of 12. So using that then, I run another simulation. And this time I replace the breast here with water. And this time I get this dose in the simulation. And then using the same calibration factor here for air, it should all be the same. If I've got the same number of photons and I agree with the dose here, then I can calibrate the sim to find the dose that I would get as if the breast was replaced with water. And so the dose that I get in milligray, just using this calibration factor and multiplying the 2, is about 4 milligray. And then what I really did measure then to test this out, I put the detector actually in the water breast, and I did actually get 4 milligray. So now I'm even more confident that the simulation could be used to give absolute dosimetry measurements, and I can replace this breast not with water, but now with different materials, different glandular density, and use different sizes as well. So that's the background of where we're coming from. And now I'll show you the results and what happened. So, sorry, I've got to first tell you about MGD, but I'll gloss over this pretty quick. Mean glandular dose was just evaluated as the kind of fraction of dose or energy deposited over mass times the fraction that actually represents the gland. So this is calculated by the G factor, and then this is used in our simulation with the calibration factor to get mean glandular dose. So it's just a fraction of that dose that hits the gland. Okay, and so in the breast, I'm actually just varying the composition, and then this is a homogeneous distribution. So the G factor just incorporates this kind of change in the gland. Yeah. So yeah, and that's just how it relates to air coma. But that's all right. I'll show you the results, and hopefully that will be a bit more clear. But that is the math behind it. And this G factor, if you look at for different, it's looking at the mass energy absorption for gland and for adipose. And so if you use a G factor here of 50-50, so half the fraction being gland, half the fraction being adipose, you see that there is a maximum kind of absorption of the G factor and maximum difference at around the 20 and 30 keV mark, which is actually the beam, around the beam energy that we're using, which is falling off a little bit there. But yeah, that's the range that we're after, and hopefully that'll help us distinguish the gland and the adipose from each other. Okay, so that's the technical side. And now I'll get into some of our results. So in this case, I did calculate the mean glandular dose according to the equation with the G factor and the energy deposited in each one of these breast sizes here, going all the way up to 20 centimeters in diameter. And then I just divided by air coma, because when we're going to bring in patients, we're actually just going to be measuring with the detector in air, the air coma. So that's something that we'll measure on the day. And then to know what mean glandular dose the patient will have, we will just need to multiply by this factor. So that's what this table then becomes, or this graph becomes quite useful, because going along, we can say, okay, well, the patient could have 25% breast composition, 50, 75, and maybe they have a 10 centimeter wide breast at the maximum thickness here at the top, the maximum diameter. And so then we would use a mean glandular factor for 25%, that's about nearly 0.7. So this just becomes a really good lookup table to predict what kind of mean glandular dose you would get in the breast. So for 35 keV, we get the same graph. So these become a nice lookup table. But what we notice straight away is that the factor that you need for 32 keV is often lower than the factor needed for 35 keV, which means there's more difference between the mean glandular dose to the air coma than at 35 keV. So that's something to note when we are converting between the two and as the patients are coming, because we do get more absorption from the breast at 32 keV. So there's more dose that can go to the breast there. So that's something to consider for larger breasts versus smaller breasts. So as an example of using this factor, here for 32 keV, I'm just going to choose this point here, the 25% for a 6.5 high breast model. So that's the height like this is on the paraboloid. And for example, for 32 keV, 25% gland, 13 centimeter maximum diameter, the MGT, the mean glandular dose over air coma is 0.6. And so using the air coma rate that we just measured the other week, we got 0.3. That means that the mean glandular dose rate would be about 0.2 milligray per second. Now, we keep this as a rate because from this, we can actually determine the total CT scan exposure time. So that just means if we want to give 4 milligray, which is actually the goal that we're trying to do to keep it under 5 milligray for us, our scans here at the Synchrotron, we would put 4 milligray then and this factor together to find 22 seconds. So if we want to give 4 milligray in 22 seconds, that will give you this dose rate. So that is how we will determine then the total scan speed that we need to use for our patients. And so what we're hoping is that in about 20 seconds that the patient can hold their breath and reduce some of the movement as well. And now you see this is why we're on a little bit of a quest to find more flux, just because for the higher breasts, this MGD on air coma factor is really decreasing. And that makes it a little bit harder to actually give 4 milligray because we need to expose for much longer. So ideally we would have more flux so that our air coma rate here can be a bit higher. So that's what we're hoping with a filter change, this shutdown. Yeah, so at the moment though, about 22 seconds. And so if we compare the exposure as a function of glandularity, so here we're going from about 25% all the way up to 100% in the simulation. And you see that it does increase ever so slightly along these lines when we're looking at glandularity. But the biggest change you'll notice is for breast thickness. So here, as we're, wrong way, as we're going from 4 centimeters to 8 centimeters in radius this time, yeah. So that's radius, so imagine times 2 the diameter. You're seeing that there's a huge change in the timing that's required. So the very, very thick breasts need a lot longer to give this 4 milligray mean glandular dose. So about 30 seconds, at least at 32 keV. So at 35, what we saw is if you draw a line at 30 seconds, most of our parameters actually end up below the line. So if we're changing radius up to 8 centimeters, or rather 16 centimeter diameter breast, you're still below 30 seconds with the current flux that we have at the synchrotron. So hopefully we can increase that and get everything under 20 seconds, but at the moment, that's what it's looking like. So I think most people can hold their breath for 30 seconds, but it might be a little bit tricky under pressure. So let's hope we can maintain that. But it does make us consider using 35 keV beams just for overall smaller exposure time when we're doing the scan. So we've now started to test that more compared to 32 to look at image quality. So yes, that is the story of the dose, at least the average dose in the whole breast. So let us see then, according to cup radius as well, I think I spoke about that already, that it's the biggest factor in the dose. But as I mentioned before, the entrance dose and exit dose wildly differs through the breast. So instead of having the average dose represented, I'm actually concerned with the entry and exit dose as well to see this hotspot in dose. And with the thicker breast, the difference between the two will be quite big. Yeah, and so that's why the exposure time with increasing breast radius is also going up because we need to expose longer just to make it through the breast to get to the other side. So it is definitely, oh, I've written over it again. The breast, oh no, that's not the eraser. The breast radius has the greatest influence on the mean glandular dose and required CT time, more so than the energy. So we need to factor that in when we're having patients come in as well. Yeah. So what does it look though for a CT? So if we look now, this bit of code that I wrote simulates the CT using one of the images. Now for 32 kV, this is what the dose distribution actually looks like within the breast. So you can imagine it rotating around in space. It's, you know, the beam is coming, this is rotating. And so all of that mostly gets absorbed in the entry, even though it is rotating, and some cooler on the exit. But overall, this is averaged out and you see for different breasts what's going on. So in the very small one, there's not a lot of variation in the dose. So there's not really between 0.18 and 0.25 or so. But as you increase the breast thickness, here you see at 8 centimeters, it's quite a cold spot. So about 1. And then at the entry, 1.6. So this is the change in the dose factor. It's quite high actually. And when we use 35 keV, we can actually bring that factor down slightly. And so for thicker breasts, we again kind of finding that this 35 keV should be used to get through these thicker breasts and actually give a little bit more balanced dose distribution to protect that entry from becoming quite different to the center. So yeah, that's what we're looking like for CT as well. Again, kind of supporting that higher energy. All right, so this has all been mean glandular dose, and now we started to look at individual gland doses. But mean glandular dose, while I was running all these sims, just seemed to me quite strange, because in planar images, this low kilovoltage X-ray energy actually deposits most of the energy within a centimeter or two. So if I just look at a single projection here, like kind of slicing through the breast. So if I draw here, this is like taking a slice like that. And then I've shown the slice here. So the beam is coming from underneath. So here it would be coming there. And you see that most of that dose is really deposited on the entry. And for 35, you can see like more of it is able to penetrate through. And that's why we're getting more homogeneity when we're doing the CT. But if we're looking at the dose, it's, in one go, if we wanted to take a single image, not a CT, to give 4 milligray, you'd need 35, 30, 40 milligray to be able to do that on the entry. So that's quite hot compared to what we were expecting. So entry dose is, of course, much, much higher than exit dose for these imaging beams. But for a CT, and this is a particular advantage of the synchrotron setup, we're able to actually combat this a little bit better because we can drop the dose that's required, because now we're doing a full CT. And instead, to give 4 milligray here, we now have in this very large breast 18 milligray on the entry, not 45. See, at the center, though, we're dropping down again because this breast is actually the thickest one I've ever simulated. It's about 20 in diameter, so it's the very biggest one. I don't think we'll be getting as big as this in our trials coming up, but just in case, this is what it looks like. So for 32, again, you see the most difference, but for 35 kV, which is this one, you are starting to see that it's kind of smoothing out, and you get about a bit over 7 gray in the middle, milligray in the middle, and then on the edge here about 18. And I should say that this slice was taken right at the top of the breast where it's thickest. If we go to the middle, you actually drop the dose below 4 milligray. But overall, the average in that breast is 4 milligray. And so this is a huge advantage of doing a CT. We can drop the entry dose to those glands down to 18 gray from 45. So that was quite an interesting finding to further protect the breast by just doing a CT. So how does this compare if we put into context with a real mammography? So of course, then I found a mammography spectra. So this is using a molybdenum target with 30 kVp energy, and they often use about 0.03 millimeters of molybdenum to filter it. And what you see is that you get about 17 or so keV, the characteristic peaks of molybdenum showing up that drive most of the energy of this beam. And it's very low. So remember, we're more like up here at 32 kV. And they use that more for the contrast between the gland and the fat. But what does it look like if we were to use this kind of spectrum on our sample? Well, it looks like this. So our air coma becomes 24 milligray to pull off 4 milligray in our mean glandular dose. So I found the MGD on air coma factor again. And that's actually really close to the literature. If you remember the maximum they were reporting in the literature, it was about 40 milligray air coma. So that was really interesting to see that we were kind of close for the thickest breast case here in this example. So that's at least the air coma. This is the average dose. But the real dose that these glands are actually seeing within the breast is actually much higher on the entry. So what is it? It's about 45 or 50 again, maybe even higher. There's some hot spots in there that are even higher, up to 50 milligray, just to be able to do a single planar image of a particularly thick breast. So that is why in the clinic, they're relying a lot on the compression of the breast, because we want to restrict it to be in about 5 centimeters or so, or 50 millimeters you see here. So that's about, to there or so. Yeah, more like that. So you want to compress the breast into that region so that all of the energy can be deposited within that bit and you can drop the dose. But here, because we're trying to give 4 milligray to the whole thing and it's quite thick, we need to drive up the dose on the entry, and that can harm some of the glands should they be placed or positioned near the entry on a real patient. So that is a bit of an issue then using the mammography spectra for thick breasts. And I can now understand from the clinical perspective why it can be not only hard to see the image, but then hard to kind of have the patient dose increase or the image quality increase. That's a very hard decision to have to deal with. So even then on the image quality, like I mentioned, it can be impacted. So here is my fake detector, and I was able to create an image based on the photons that entered the detector. So here you see the background image is actually composed of most of the photons here, making it without anything in the way. And then here, the photons here are counted after passing through the breast. And it's very, very low. It's actually not 0, but it's way down here, like 10 times, or maybe a million, or yeah, about somewhere from 1 million to 10 million photons actually made it through there compared to 160 million. So the image quality is not that great in this setup. So you really do rely on compressing the breast then in that case. But how do we compare? If we try our 35 keV mono beam with the synchrotron, dose distribution just through one projection, so just one look before we rotate our sample for the full CT, just one quick look, you can see if I had to give 4 milligray in that one look, I would need on the entry for this particular sample, I would need about 20 milligray. So it's not as wide as the breast example I gave before. It's not the 20 centimeter breast, so we don't have to use that much dose. But it's more like 20, 23 milligray compared to, what was it on the other slide? 50. So we're half the dose that's required just because we've changed the energy spectrum. So in this case, the MGD per air coma factor is about 0.65. And so the air coma rate that we need to give 4 milligray in the full CT scan is actually only 6, which was really interesting. So in that way, when we actually run the CT part of the code, and this would be then the image that we really do acquire, we're not acquiring that one, we're doing a full CT. Instead of having 25 milligray, we're now looking like 12. So it's much, or maybe 10, 11, yeah, so much less. And the homogeneity has improved as well. So you're getting a kind of equal, more or less, distribution across the breast. And this is in the top slice of the breast. Now, toward the middle, we're dropping down in milligray because remember, the average is 4 for the whole breast. So that is what's going on inside. And this is the image. And so we can now distinguish a lot more in terms of the breast because it's able to pass through with this kind of energy in our current setup. So we don't need in this setup to compress the breast as much is what I took from that, because we're able to kind of get through the breast and using the CT, we can actually reduce the dose that's needed to do it. So that was really promising and gave me a lot of hope for this method to really use a CT just for preserving and reducing the complication of the normal tissue. So yeah, and a bit of an extra as well, I was also with the simulation able to look at the detector efficiency because I noticed, well, I'm counting the number of photons that's going in. How does that correlate to the real number of counts that the detector is making? So my pixel sizes were set to be the same as the real Eiger detector that we use, same distance and everything. And I looked at the photons that were detected per milligray, or per 1 milligray. And experimentally, with the help of Yakov, I looked at that data and it was Eiger counts per 1 milligray as well, same pixel size and everything. And so I was able to plot photons per milligray per pixel. And this is the real measurement using a 16 keV threshold on Eiger. So setting the threshold to the recommended half beam energy, and we're using about 32 or 35, so about 16 keV is half. That's what we get. Then with the simulation, this is what I get. So I was like, wow, that's really cool. And the Eiger detector is actually a photon counter. So I found that it was actually very, very efficient to be pretty much bang on what my simulation predicted. But messing with that threshold tends to change things a little bit. So what I noticed was when we set it to a low threshold, you're asking it to pick up more counts from the main pixel, but even pixels around it too. So I saw the efficiency dive up to 200% now instead of 100%. So 16 keV remains at around 100% efficiency. And then if you cut off more photons by increasing the threshold, you do drop the efficiency down to 50%. So I found that the sim then was quite powerful in recreating the image that we see on Eiger, considering that when using the recommended settings, that it really was pretty much 100, like 1-to-1 or 100%. So that was really promising. Yeah, so that's just the plot of threshold with the average efficiency of Eiger, and you just see it change for about that mid-half energy of our beam. Yeah, so a bit of a side interest project, but it just gives me more comfort that the sim is really representing what I have, and that I can put different breasts in. So yeah, so my first summary then for this massive amount of simulation and dosimetry work is that I can confidently say that I feel like we can really estimate the synchrotron CT mean glandular dose ahead of upcoming patients using this sim. So we can vary the patient breast size, we can also vary the beam energy, and using the absolute dose calculations, like calibrating the simulation, we can actually validate it and say, yes, that was checked with the real measurement and we are getting an agreement. So that was really promising to be able to vary the patient kind of properties coming in. So our breast cups that we provide for the Synchrotron project some of them have already been implemented into the simulation to determine MGD and the scan times that you would need to deliver that 4 milligray. So that's already been used, and hopefully we will see that that translates to good image quality as well. That's kind of the next part of it, is to see how that goes with image quality. But I'm hopeful that we can investigate that further and do a good job. But a major thing I really wanted to note from this was that our CT scan can produce at least 5 times less dose on those entrance glands for a 4 milligray scan compared to a mammography or a planar image. That was really powerful, and I thought that's a really good advantage of potentially doing a CT over a planar image. So yeah, so that is my summary of simulation and dosimetry. So thank you so much for those in the audience that are not used to seeing so much physics and simulation and so on. But I hope you could follow along and see what was happening there, because now I'm going to change tack and attempt to do some more of the imaging side of it. But as I mentioned, it's a little bit less in my area compared to the treatment planning and dosimetry. But here we go. So this is the kind of second effort that I was involved in to look at how we could model patient breasts and actually see if we can model this difference in the breast density, different breast sizes, and how that could affect or potentially impact the image quality. So this is an example here at the top of planar X-rays here detected from normal mammography. But down the bottom left is actually a 3D rendering of our Synchrotron CT. So I've just kind of projected all of the images together and then rotated them in 3D, so you can see all the kind of information that we're able to get out of a 3D scan. So how could we potentially model this difference that we're getting between? So what we did was we developed that anthropomorphic phantom that represented, it had egg white representing glands and pork fat to represent adipose. So my question to you guys is, which one out of these two samples here side by side, one is a real mastectomy and one is the anthropomorphic phantom? Which one do you think is which? I don't know if anyone's brave to have a guess. Anyway, left or right? What do you think? Oh, I can't even see the chat actually. Maybe I have to look on Chris's screen. What do you think, Chris? Do you know the answer?
Andy Clulo says real is left.
Real is left? Oh, Andy, is it? Yeah. Well, Andy, you would be completely right. I think you must know what you're looking at. So when I asked a few people, I did get a bit of a 50-50 chance. But yes, you'd be right. The left is the real mastectomy, but the right is the anthropomorphic phantom composed of egg white and lard. But the major difference is just the number of holes that you get in there because of the pork fat. It does tend to have a couple of holes in it when it sets. So I'm still working out how to eliminate that. But it's really been quite nice to represent the randomness of the gland. And in terms of the contrast, it's looking quite good. So this is it from side on, looking at the mastectomy on the left and the phantom on the right, and with the synchrotron resolution, and then with the clinical or conventional CT resolution as well. So I was actually able to scan it on the CT just across at Monash. So thank you to Monash for that one. But it's been quite nice. So these are not the same, it's just different samples. So total different sample. This is about 25% glandularity. This one's more like 8% or so. And it's looking quite nice to try and mimic the mastectomy. So how do the CT numbers hold up? Well, in Hounsfield units for the egg and gland, I'm getting about -20. For fat, I'm getting about 95 or so. And the real breast for 50-50 glandularity is just over 25 as well, maybe 30, a bit more. And then adipose in one of these Sears phantoms, so kind of plastic adipose, is about -76 or so. So I'm getting a little bit of difference, but I think it's because of the air. So as we're heading toward -100 HU, I think it's the air mixed in the lard that's mucking that up a little bit. But it is nicely between these two ranges, within the range of our standard breast phantom that's commercially available. So here you can see the Hounsfield units or CT numbers used for the different components on the breast phantom, from -100 to -25. So it's been quite nice to compare to when we're looking at imaging with this kind of commercialized phantom as well. But ours is a lot more interesting because of the randomness and the representation of breast density. So in that vein, you can see that here I'm able to not only vary the diameter of the breast, but also the glandularity. So that's been quite beneficial as we're looking to assess image quality due to different breast thicknesses and different breast density. So that's why we developed the phantom, and it's already been used quite a lot to pull that off, and it's been quite promising to do so. Now, an image quality analysis is a very fast one. Like I said, it's not totally my area, but I had a go. In this case, I looked at signal to noise ratio and contrast to noise ratio between the gland and the fat. So if I looked at it in a real breast, where the image was taken at the synchrotron, and then the anthropomorphic phantom breast, and then also the anthropomorphic phantom for a clinical CT with a high pass filter and a low pass filter, so different reconstructions. So what did we get? Well, signal to noise generally at the synchrotron I actually found was quite good. And so I should also point out that the resolution is very different as well. And the energy, of course, here would be about 32. And then this one is more like 80 kVp. So a little bit different, more of a spectrum in energy, this one compared to the mono energy or the straight line 32 keV. So with that way, I think I'm getting more signal to noise ratio because it's able to distinguish between the signal better because of the resolution and the synchrotron, probably the lower energy. So that was quite nice to see. But with the right reconstruction, it seems anything is possible. So with the CT, the clinical CT, we are able to try and recover some of the signal to noise just with a different recon. Now for contrast to noise, contrast to noise ratio, I am getting a bit lower on the synchrotron, so that was interesting to see, but it's similar to the first approach on reconning on the clinical one. So I'm hoping that with enough processing in terms of our synchrotron images, we might also be able to recover more contrast to noise. And maybe that's where we could play with the energy a little bit more as well and try and optimize some of our other scan parameters to improve that. But as a quick look, I'm actually pretty impressed. And another take home from this data is that between the real breast and the anthropomorphic breast, I'm getting a very similar result between gland and fat and the gland. So they're, even to the imaging side of it, they're looking like they're approximating a real mastectomy or real gland situation. So despite the air pockets that I'm getting. So yeah, so I think the phantom is working quite well. It's been quite a good representation of the randomness, as I mentioned, the gland distribution. and the breast density to assist us in choosing the right clinical image acquisition parameters as well. So what MGD or mean glandular dose do we need? What is the timing going to be like? What parameters do we need to set on our detector? So that's been quite nice to choose as well. So here is a 3D rendering of the breast. Here is again the real one. That's the real one. And this is the anthropomorphic phantom. So yes, they look a little different, but I'm hoping that the randomness of the gland distribution will help us to choose our parameters and mimic the correct density of the phantom as well to get our image quality right. So that's pretty much all of that. And the summary here is that already this phantom has been proven useful. We use it side by side often with our mastectomy samples that come in, which I'm very proud of. So I'm glad it's useful to them to compare with as a very kind of basic and something you can make home model of a breast. So that's been quite good. And I hope that now we can link image quality with the mean glandular dose using this work and the mastectomy work to bring both sides of this story that I've been telling together. So that's the kind of the next and last step, is using the mean glandular dose parameters that I've already got. How does that translate to the image quality with different breast density, with different breast sizes? So that would be the final steps of that. So yes, in my conclusion, thank you so much for staying this long and listening to me. I'm very happy that we can estimate mean glandular dose. That was a major goal for this work, according to really personalizing the patient, like size and the density of the breast. And planar, so a single image versus CT, is very different. And I'm so glad that we can see that we've reduced potentially these doses that we need to give to the patient breast just by doing a CT. So that's been a really nice thing to find. And I hope we can further determine the optimum conditions for image quality as we move forward. And personally, in this project, I've been very excited to be a part of it. And I'm very much looking forward to a positive change in the breast imaging experience that will be less painful, so no compression, and has less false positives, to be able to see through the breast density or thicker breast, where it's much harder to do so in the clinic. So thank you so much. These are my acknowledgements. I have a lot of people working and helping me out, getting these images and doing that. I just definitely like to thank my master's student, who's been doing this work as well on the simulation side. So here she is at the user meeting presenting her poster on this data. So thank you so much for your attention. And yeah, I'm happy to take any questions at this point. Thanks.
Thank you so much, Elliot. That was a fabulous talk and quite comprehensive, and also very, very beneficial to the clinical studies that we are going to do. It is unfortunately 5:30, and I'm quite sure many people have to leave, but I have lots of questions, and I'm sure many other people. So if you don't mind, we will share your email address, Magdalene.
Yes, please, no problem.
We will be in touch for further discussions.
No problem at all. Sorry, guys, to go over time. Thank you so much.
Thank you. Sorry, team, is there anything urgent you want to ask? Because
sorry, Amir, did you say that we need to finish the seminar anyway?
The seminar was for 1 hour, but I don't mind if you want to stay online, but I understand many people may want to leave.
Right. I definitely had a couple of questions which I wanted to ask, but I can do it some other time.
I don't mind as well. I don't mind. I'm happy if Amir, you're happy. Yeah.
So can I ask something now, Amir?
Sure.
All right, thank you. First of all, Lilette, brilliant talk, brilliant. Thank you so much. I'm very impressed, really.
Yeah, thank you.
So just maybe silly questions. Firstly, about your model, you compare the Hounsfield units between the breast tissue and your lard and egg white. But there's two other important parameters that perhaps worth looking at later.
Yes.
Firstly, because we are doing phase contrast imaging, we in principle need to check not just beta, which corresponds to absorption, of course, but also the phase shifting properties, right? We need to somehow be able to assess the similarity in delta. Hello?
Yeah. I can hear you. Yeah, no worries.
Yeah.
No,
so that's one point. The other important point, which we certainly had in mind previously with respect to other phantoms, is that the sharpness of the interfaces between, in this case, different components like your LART and your egg white, the interface is also critically important, because that will determine the degree of phase contrast, right? So if it's too sharp, that's bad. If it's much less sharp than in the breast, it's also bad. But by the look of it, you're close to the right sort of a sharpness of those interfaces. But that would be interesting to check sometime as well.
Definitely. No, thank you, Tim. I'm a bit out of my depth for phase contrast, just because it's definitely not my area. I had to play with these parameters while I was reconstructing earlier on. But I did notice that, especially in the air pockets that I get in my Phantom, I am getting more of that interface effect. So that is something I noticed, are getting more shiny, which can disturb the image. But if I downplay that, it was quite good and quite in agreement with the mastectomy sample. So
with the air pocket, which is indeed the most obvious difference in the features, maybe you can use some sort of annealing. I don't know if it's possible.
I think the factor is heating to try and get rid of the air pockets from the adipose while it's sitting, or sorry, rather the fat while it's setting. So that's something I've been working with to try and eliminate them. Yeah, I've noticed for more heating, they do tend to disappear. So
thank you. Sorry, I'm just conscious of the time, so I'll just.
I know. I'm so sorry. I'm so sorry.
The other issue is the image quality. It's we have been working a lot on it with Amir and others. So it is certainly not sufficient to just compare the SNR.
Yes, I wasn't not sure.
Again, something we certainly can discuss in more depth later. But one needs to look at the spatial resolution as well as a minimum. So you already have contrast and the signal to noise covered, but you also need to simultaneously look at the spatial resolution, because otherwise one of these two quantities in isolation doesn't have much sense by itself. You need to look at both in comparison. And I think that's where our synchrotron images are already ahead, looking at
you can see the difference. It's like a haze.
Something we can discuss. And just a very quick final point. You raised this very important issue, which I wasn't aware previously, about the difference in the entrance dose between the conventional mammography and our CT approach, right?
Yes.
But what confused me a little is that when you were talking about quote unquote conventional mammography, you didn't seem to take into account the fact that the breast is usually compressed.
Yes, so I do in a way by looking at the dose distribution. So I can see that if we compress the breast from this level, which is about let's say 6 to maybe 4 centimeters, then the dose distribution is very much still quite high. So that means you can drop the dose to better get 4 milligray within this region. And that's often why they're needing to compress the breast, because if you leave it this wide, you see there's such a difference in the dose because you're depositing everything on the entry and nothing makes it to the back. And so when you're averaging over this to get 4 milligray, which is the standard, they're looking at the average, you need much higher entrance dose, which is potentially leading to complications in the breast tissue. So that was something I really saw, was you really need to compress the breast here into something more like 4 centimeters to resolve that.
I understand that, Elia, this I understand reasonably well. So when you do this, when you present this comparison, and I think it's very much worth a publication in the near future, but when you present this comparison, I would say you certainly need to do the comparison with the compressed breast.
Good idea.
Slide, you showed this large variation in the compressed thickness, right? So when you compare different breasts, you will need to take that into account, and probably as well as the change in the density when the breast is compressed. So
definitely, I have yet to simulate the compressed breast
otherwise
setup.
It won't look like a fair comparison, I think.
Okay. Oh, I was going more for a fair comparison with if you did the same beam on our setup, what would it look like? But yeah, I can do the compressed case for sure. That's more closer to reality. Yeah, thanks, Tim.
Thanks a lot, and a great talk again. Thank you.
Thank you, Tim. Thanks.
Okay, is there any other urgent question? I saw something in the chat box from James. James, are you still here? Okay, I can read that. So it's basically about the dosimeters used for calibrating the simulations used air karma values, how the air karma values rather than absorb those values measured in GINT for simulation.
How are they different? Was that the question?
How the air karma rather than absorb those values measured in the software.
Okay. No worry. So in that way, what we did was we actually calibrated our farmer ionization chamber, PTW farmer chamber, for air coma calculation or measurement rather, and also for water. So then we have a calibration factor unique to that device that we can use when it is in water or it was in air as well. So that way, we get the real measurement. We do all the corrections for temperature and pressure in the room, and also recombination and polarization on the chamber as well. So this is a clinical way. We do this for also my radiotherapy work, but just a different ionization chamber. So that's how it is calculated. And then, I measure the air coma, run it in the simulation, same setup with air. And then from this, I extract the calibration factor that talks to, or speaks to rather, the simulation in terms of the X-rays to get that air coma, or the X-rays to get that dose in water. Yeah, I hope that makes some sense.
If you wouldn't mind me just expanding on that question a little more, if that's okay.
Sure, yeah.
My understanding is that often in GIANT4, you might use like a sensitive detector or something in order to measure the dose deposited within the sample at any given point. From my understanding, the dose deposited in a point can often differ from the air coma value, which is the energy released.
For sure. Yes.
How do you account for that in the simulations?
That's exactly right. That's exactly right. So in that way, in my sim, I still measure within the same volume that the detector would occupy. And I'm looking at the energy deposited within that volume, and then the energy exchange in the case of air. Using an approximation I found for these kilovoltage energies, that the air coma is equivalent to dose in air. So I have found that for these energies that I'm using, they're using that approximation. So in that way, I do have a sensitive volume in GIANT where I'm scoring this, and in the case with water and in the case with air. And then I'm using this approximation from the IAEA. Yeah.
Oh, I wasn't aware that was the case. Is this
I was surprised as well. I think only for the low energies. So I was like, oh, that's nice. But I did also take the approach of looking at like kind of the energy transferred and then leaving it as well. But I found I didn't need to. It was almost 1-to-1, a little bit different. But that's why I thought, so they are able to do 1-to-1. I was like, I get it now. That was really interesting. Yeah. And from all my data, I've found that it is agreeing. So when I do use the calibration for the air using this approximation, then I am getting the same, I get the same result in water, which is really nice. So I was able to confirm that it's working, talking to each other when I use it. So from air to water, and I do get the same measurement, at least within, a kind of acceptable percentage. Yeah. So it was interesting.
Okay, that's very interesting. I've been doing simulations for much higher energies, and I would have thought that
then it matters. Then for sure. You can't get away with it.
I've been thinking about a way to score it as energy deviation of the beam rather than deposition to the sample. But that's a separate me problem. So no worries.
Good luck. I know, I feel the pain for higher energies. Yeah, thanks.
Yeah. Okay, I'm a bit really mindful of time because this discussion can continue forever. But we will definitely be in touch, Elliot. For example, Jenna, I don't know if you have met each other before, but Jenna, as part of her PhD, is looking at the effect of glandularity and image quality. And we will definitely be in touch to arrange follow-ups and meetings.
No worries. I'm so sorry to go over time.
Work.
Yeah, thank you so much. It was really an honor to present, and thank you so much for the invitation, and to Magdalene as well, who chased me very well to get me to come. I really appreciate it and the opportunity. So that was really great. Thank you. It's been nice to see this work kind of come through and then be able to show you. So yeah, thanks.
Yeah, thank you everyone, and nice evening.
Yep.
See you next month. Bye.